Welcome to today's session titled One Shared System for Concurrent Engineering. My name's Steve Shaw. I'm a product manager at PTC in the PLM segment, working in the design engineering group where we're responsible for our CAD integrations as well as visualization, among other things. Today we're going to talk a little bit about concurrent engineering. What is concurrent engineering? We'll sort of level set with the definition. Then we'll talk through a few examples of how PTC's products can enable or facilitate concurrent engineering, along with expressing some of the benefits associated with this concept. So what is concurrent engineering? This simple diagram depicts a basic sequential product development life cycle, if you will, where things evolve from concept design through to detailed design to simulation to manufacturing and production of the product, all the way out into operation and service. In a sequential engineering process, these things happen in sequence. One activity or one phase doesn't start until the previous one has completed. Concurrent engineering, as you can well imagine, is taking that concept and compressing it and developing processes that will enable these various phases or activities within the life cycle to occur in parallel or as close as possible to parallel. By having these activities ongoing concurrently, this presents an obvious opportunity for reducing your development cycles and reducing the overall time to market for a given product. But this doesn't come without complexities. This type of processes or initiatives require tight coordination and collaboration between the various people representing the various states and disciplines associated with the overall development process. It requires that these different stakeholders have early visibility and input into the development process all the way back into its earliest phases in concept and detailed design. It requires tight and repeatable processes to orchestrate the various activities associated with these various disciplines. And given the complexity of such processes and the data associated with many products today, it requires the underpinnings of robust technologies to support the data and activities associated with concurrent engineering and its initiatives. During today's presentation, I'm going to highlight three simple examples of how PTC can help to enable concurrent engineering in the area of detailed design, simulation, and manufacturing. But before we do, I'd like to talk a little bit about the economics of product development. This is just a generally accepted diagram that depicts the product development costs as it evolves during the product's overall life cycle. And you can see in this chart, as depicted by the yellow box on the left-hand side, that nearly 90% of an overall product's cost is incurred even before you start production, the actual manufacturing. There's this sunk cost that's associated with the development cycle itself. This means that if you recognize issues late in that development process, there can be a significant impact and cost associated with making those types of changes, as a high degree of cost has already been incurred or committed at that stage of the development cycle. Concurrent engineering promotes this ideal of identifying potential issues as early on in the development process as possible by, again, having the various stakeholders and disciplines involved early on in the product planning and development process. With their involvement, by identifying changes early in the process, or sort of in the lower left-hand corner of that yellow box, you have an opportunity to really help drive down the overall costs of your product. So there's some real economic benefits or potential associated with having such concurrent engineering initiatives within your company. And PLM certainly is a tool that can help facilitate these types of concurrent engineering processes and activities. It provides a rich environment to capture the overall digital product definition and make that available in all of its various assets available to all of those disciplines that are involved in the product development process, whether it be quality, manufacturing, service, marketing, and even sales, who might have potential input into the overall product design and definition and early concepts. It has a robust set of capabilities to provide governance, to facilitate or implement repeatable, reliable processes to help facilitate the efficient communication and collaboration and traceability of activities related to your product development lifecycle. And it includes robust visualization support so that these downstream stakeholders can visualize and interrogate and provide contextual feedback regarding design ideas directly within the system, again, early on in the process, so that can be captured and accommodated to facilitate more efficient collaborative development processes. So let's take a look at our first example. Windchill PLM has robust capabilities that support a multitude of CAD tools, but also facilitates multi-CAD product design itself. Not all products are mechanical in nature. Many of them have software and electrical components that need to be accommodated and associated together to provide that complete digital product definition that we mentioned earlier, and allow those CAD designers to collaborate, but also provide visibility to those downstream stakeholders, allowing them to leverage Windchill's capability for finding and reviewing and visualizing and commenting on the designs as they evolve early on in the process, and deliver that feedback in a bi-directional manner back to the designers for incorporation into their product. Now we're going to take a look at a quick example of this notion of multi-CAD collaboration. Here, as a Creo designer, I'm working on a multi-CAD design of this circuit board. You can see that it actually has a component in it that's actually not native to Creo. It's a SolidWorks subassembly for this particular cooling fan to cool the processor. But in this case, I'm actually collaborating with my electrical engineering colleague, where they are sharing design changes directly with me, or incremental design changes directly with me, where I can evaluate their proposed design changes. In this case, they intend to incorporate additional capacitors onto the circuit board, and these capacitors have physical dimensions that the mechanical engineer has to be aware of to make sure that it doesn't interfere with any other mechanical components that might be present on that board, but also doesn't interfere with perhaps any enclosures that are surrounding the circuit board in this case. So once I've incorporated those changes delivered to me by that electrical engineer, I can check that information back into Windchill. And when I check this mechanical design back into Windchill, the corresponding visual files or visualization content will be created. The engineering bill of material will be updated with this information. And now the rest of the enterprise has insight and visibility into the current state of the product design. They can evaluate and trace the various design artifacts that are associated with this product. In this case, there's an assembly, but also that ECAD schematic that defines the board. In addition, we have information coming from maybe a supplier, for instance, who provides this cooling fan component that may have been actually authored in a non-Creo tool, in this case, SolidWorks. So MultiCAD collaboration between different design disciplines, in this case mechanical and electrical, enable these two different disciplines to work easily in a concurrent fashion to deliver product updates to one another and promote that information within the PLM environment so that other disciplines can access that data. The next thing I'd like to talk about is simulation. Windchill certainly is capable of supporting simulation-related activities, and given its the high variability of simulation tools that are used out there by typical customers, it has the flexibility so that you can configure the system to manage and manage the various outputs coming from those tools, whether or deliverables, including final results and other artifacts associated with simulation. We also, of course, provide native support for the embedded simulation tools available within Creo. For instance, Creo ANSYS Simulate, which puts robust solvers directly in the hands of in the Creo environment itself. But not only do we are able to manage the content associated with simulation and relate that back to the original product design data, we also have the flexibility to tailor the system to support the processes associated with simulation itself, whether that be orchestrating or facilitating the handoff of design data off to the analyst at the right point in time of design maturity, but also to capture that output and results from the analyst, as well as the approval of their findings back into the system, so I have full traceability as it relates to the activities of the analyst, so that everyone has an understanding of what was analyzed as it relates to the design, but also to the upstream requirements that were defined for that given product. Now, simulation is a complex activity. It's typically something that is done by an expert. They typically take copies of the model and create their simplified version to efficiently facilitate the detailed analysis that they perform. But at the same time, the design itself may be evolving. So if a design change is introduced in the middle of a simulation activity, that can be disruptive, as you can well imagine. So one of the concepts we advocate at PTC is this notion of simulation-driven design. Imagine if the designer themselves could be informed by simulation results while in the process of developing the product. This idea of simulation-driven design is realized with the introduction of Creo Simulation Live, where we have integrated the ANSYS Discovery Solver directly into the Creo environment, which truly allows for real-time design guidance from the earliest stages of conceptual design. Let's take a quick look at what that actually looks like. In this case, we're going to look at the rear arm of the suspension on this motorcycle. In this case, directly on the originating model, the design engineer is able to apply constraints and boundary load conditions to the design data, and in real time, they're able to Simulation Live is able to provide analysis or performance feedback on that given design, whether it be stress information or deformation information. Now here I'm actually going to make a design change by changing the profile of this rear, I guess, swing arm of a motorcycle. I'm not sure that's the right term or not. Just changing the profile from one with a rounded top to a more rectangular, tubular profile. Again, immediately after accepting these changes, the analysis results are updated, providing the design engineer guidance as to what the implications are as it relates to the design decisions they've made in conjunction with the loading conditions prescribed by the originating requirements. So this is a really powerful capability that truly takes this idea of concurrent engineering to the next level by combining design with analysis. It allows that engineer to make highly informed decisions while developing their design ideas from the earliest stages to the later stages of their development process. Truly an example of concurrent engineering. Now that, of course, doesn't replace the need for an analyst to perform their high fidelity simulations that they traditionally do, but it certainly provides a higher degree of confidence in terms of what kind of results you're going to see, and helps to eliminate that highly iterative back and forth exchange that historically has gone on between engineering and the analyst community. So next we're going to take a quick look at manufacturing as another example for concurrent engineering. In this case, we're going to talk a little bit about model-based manufacturing, planning, and execution. Again, because of the high degree of traceability that is provided by Windchill PLM, it enables the manufacturing engineer to directly access and transform information developed in design engineering to begin some of his or her planning activities early in the process, whether that's developing the manufacturing bill of material and transforming that information to a bill of material that's consumable in the manufacturing world, or developing the corresponding process plans that will be provided to the shop floor worker to execute the manufacturing of given components and parts and whatnot. So we're going to take a quick look at how that can be facilitated and enabling that collaboration between engineering and manufacturing. In this case, we're going to start off in Creo, where we're looking at this spindle design. Various view states and annotations have been created by the design engineer. Here, he or she indicates a critical dimension to manufacturing for this bored hole here by designating that as a control characteristic. That information is no longer buried within the design file itself, but it's externalized and exposed to the manufacturing engineer as well as other downstream stakeholders. Maybe quality engineering will look at that information to uh, determine, failure modes or I should say risks and reliability associated with the product design. But we're going to look at the manufacturing case here. In this case, the manufacturing engineer again has access to that through rich visualization to the detailed design, including the view states containing these annotations. He or she can select those control characteristics as they were originally designated by the design engineer and incorporate those into the manufacturing view of his or her parts and create a corresponding process plan to define the instructions for the production, or in this case, the inspection, post-production inspection plan for this given spindle. After creating the inspection plan, the manufacturing engineer will then begin to add the detailed steps required to complete the inspection of this particular component. Here they're inserting a specific operation, and for this initial operation, the control characteristic that was exposed or designated from the originating CAD design can be incorporated. From here, the manufacturing engineer can then publish a set of work instructions in the form of a document, or conversely propagate that information directly to the shop floor's workers' workstation in the form of a set of visual instructions using operator advisor. Now, this is not just a one-way propagation from design down to engineering. If the manufacturing engineer were to encounter a problem or identify an issue, he or she could create a problem report, initiate a change, communicate that information as it relates to the original design back to engineering, and the updates could be made, and that design change and information could quickly be propagated back to manufacturing and reincorporated or updated in the form of their process plan. So all of this is connected and traceable via a digital thread, if you will, to facilitate this concurrent collaboration between the various disciplines and stakeholders. So those are just three simple examples that are illustrative of concurrent engineering. There's certainly some tangible benefits as it relates to PLM and concurrent engineering by compressing or running these various activities in a concurrent fashion. You certainly have an opportunity to speed up your time to market, providing visibility to these downstream disciplines early on in the development process, enabling them to provide that early feedback is a recipe for improved quality. And certainly by identifying issues early in the development process as it relates to all the various activities and discipline, whether it be manufacturing or even service, you have a real opportunity to help reduce the overall cost of your product and any costly rework that might be associated with a late design change, as we spoke about earlier. But you don't have to take my word for it. We have several examples of customers that are really seeing high degrees, double digit, if you will, levels of impact as it relates to their product development process by breaking down the gaps that exist between these different stages in engineering and aligning with your manufacturing, supply, and your broader ecosystem. It's a real opportunity to get meaningful gains as it relates to your product development processes. Jabil, an electronics contract manufacturer, they're now able to take on 4 times as many projects as they did previously. Nidec, a Brazilian manufacturer of refrigeration compressors, has seen a 40% reduction in the cost of poor quality. So quality has improved because of the collaborative nature of concurrent engineering facilitated by PLM. VW, a well-known auto manufacturer, they've seen a 25% reduction or decrease in their time to industrialization, which, that's faster time to market. So PLM facilitating concurrent engineering certainly has the ability to drive meaningful impacts within your organizations. That's all I have for today. I hope this was informative, and I look forward to speaking to you again. Thanks.